Thank you, Bodhi, and good evening, everybody. Today's topic, as Bodhi just said, is the wind design provisions of BNBC 2020, which are based on ACE 705, the 2005 edition of the US standard titled Minimum Design Loads for Buildings and Other Structures. It is a vast topic. To cover it in 2.5 hours is a huge challenge. So I will do the best I can, but there will be time pressure all day. Despite the time constraint, I would like to start basically from scratch. I think that makes for better understanding. I will not spend too much time on this prompt material, but I want to start here. So wind loading is the effect of the atmosphere passing by a stationary structure attached to the Earth's surface. All structures, maybe not all, but most structures are stationary. They are attached to the Earth's surface, and any structure we put up stands in the way of wind. So it obstructs the free flow of wind. And so the wind does things to the structure. And that's what we as engineers have to deal with. Wind loading is the effect of the atmosphere passing by a stationary structure. Wind loads are controlled by atmospheric and aerodynamic effects. Atmospheric effects have to do with the weather, essentially, have nothing to do with the structure. Aerodynamic effects, on the other hand, have everything to do with the structure, nothing to do with the weather. The three terms in the general equation for wind, this you will see is the basis of most things we do. P, the wind pressure, is equal to Q, the velocity pressure as we call it, times G, the gust effect factor, and C sub P, the external pressure coefficient. Of those three terms in the basic equation, Q, the velocity pressure, has to do with atmospheric effects. It doesn't have much to do with the structure itself. The external pressure coefficient has to do with aerodynamic effects. The structure is everything when it comes to C sub P. The atmosphere does not play any role. G, on the other hand, the gust effect factor, is a combination of both. It is affected by atmospheric effects as well as aerodynamic effects. When we say atmospheric effects, that has kind of two aspects to it: meteorological effects and boundary layer effects. Meteorology, I think we are all familiar with the word. It has to do, so meteorology provides a description and explanation of the basic features of atmospheric flows. A discipline within meteorology called climatology deals with the prediction of storm conditions at a given geographic locations. So when we see the word climatology, it has to deal with the prediction of storm conditions at a given location. The climatological effects that we as engineers have to deal with in designing our structures properly are thunderstorms, tornadoes, cyclones, which in this part of the world are called hurricanes, and special regional effects. Those like in mountainous areas, wind is modified by the topography, and that is something we have to deal with. So thunderstorms, tornadoes, cyclones, or hurricanes, and special regional effects. When we say thunderstorms, it means a variety of associated wind phenomena. It is kind of an umbrella that holds a lot of different storms. Predicted thunderstorm activity controls vast majority of US wind loads. That probably is not true in Bangladesh. I don't quite know, doesn't seem that way. But in the US, most of the US, the wind is dominated by thunderstorm activity. And because of that, that is the exception to that is the hurricane coastline, which is the eastern seaboard and the Gulf Coast, the Gulf of Mexico coast. Anyway, so because thunderstorm activity controls the vast majority of U.S. wind loads, most of the inland United States has very similar design wind speeds. That has always been the case. It is only on the hurricane coastline that you see different numbers, different wind speeds. Bangladesh has much more of a variation, as you will see. Design wind speeds do not include the effects of tornadoes. That has been true until in AC 722, things are going to change. Tornado is being brought into this, tornado design is being brought into the standard, but we obviously won't go there today. And AC 722 is barely out. The electronic version is out, printed version is not out yet. So it is brand new, not adopted by anybody, just developed. Design wind speeds do not include the effects of tornadoes. Probability of occurrence at a particular location, probability of occurrence of a tornado at a particular location is so low that tornadoes do not appear in the 50-year statistical storm data used to formulate the inland portion of the map. So you will see in subsequent discussions, we are dealing with 50-year return period wind speed in AC 705 and BNBC 2020. Tornadoes are localized in time and space. They typically hit a small area. Small is obviously relative. When a community is hit by a tornado, it doesn't look like a small area to the people in that community, but on a larger scale, if you compare to a cyclone, tornado is very localized. It cuts a narrow path, and it is also very localized in time. It hits and then it goes away, and the period is so small. I think the key thing is localized in time and space. It's very local geographically, small area. The areas around them are unaffected, and it happens once in a while for brief periods, and it really is once in a while. The chances of a particular location being hit by more than one tornado is pretty remote, and because of all these reasons, in 50-year return period wind speed, tornadoes simply do not feature. They are too localized. Okay. So tornadoes have not been considered in developing the basic wind speed distributions. I think all of you have seen these pictures. These funnel clouds are very characteristic of tornadoes. And when they touch down, that's the word that is used, they can cause devastation locally. That's the all around, not much will happen, but it cuts a narrow path along which there is pretty much total destruction. Hurricanes or cyclones, on the other hand, like earthquakes, happen in some parts of the world, do not happen in other parts of the world, and that is what is shown on this map. In the United States, plenty of hurricanes on the east or Atlantic coast, but there are no hurricanes on the west coast, the Pacific coast. Down in Mexico on the Pacific coast, there are hurricanes, or if you go down to South America, there are hurricanes, but the west coast of the United States does not have hurricanes. Bangladesh is smack in the middle of hurricane alley, or cyclones, as they're called in the tropics. So it is a huge problem, as you know. I don't have to tell you. So hurricanes are, I don't want to say localized, but they happen some places, don't happen in other places. Bangladesh definitely is among the places where cyclones are common. We also have a hurricane season. They typically do not happen around the year, at least in this part of the world. That seems to be changing with climate change and everything, but typically the hurricane season has been from July to October, November, as you see on this figure. Okay? If you include hurricanes and tropical cyclones, then the season gets longer. But still there is a season. There is a quiet part of the year when these big storms do not happen. In the Indian Ocean, north of the equator, tropical cyclones can form throughout the year on either side of India, although most frequently between April and June and between October and December. So that would be the cyclone season in Bangladesh, most frequently between April and June and between October and December. On the east side of India, obviously, is the Bay of Bengal. On the west side, it doesn't concern you, is the Arabian Sea. And both sides, there are cyclones. These storms, cyclones, hurricanes, whatever you call them, are huge. Tornadoes, I kept on saying, are localized. A hurricane can cover, sit over many square miles. Not all of them, but some of them are very large, and they move very slowly. Unlike tornadoes, come and go. A hurricane can just sit there for days or move extremely slowly. And as a result, a huge area can be affected by a hurricane or a cyclone. And so these are problem storms in parts of the world where they can happen. They are very difficult to deal with in many ways. Obviously, when they hit the human side, providing relief to people who have to evacuate their homes and things of that kind. But from a structural point of view, to design structures that will stand up is a major challenge. Bangladesh, the last cyclone of significant size, I believe, was the one on the 4th of May of 2019, Cyclone Fani, originated in Orissa. I don't know if it originated there, but that's where it gained strength, and then came through West Bengal over. I don't know that it went right over Kolkata, but close to it, and then Bangladesh. But it spared Dhaka. It went to the northwest essentially, so there wasn't a whole lot of effect of the storm. But this was a significant storm in 2019, May of 2019. The building code enforcement project that we are doing for the World Bank. This is from the terms of reference of that project. And I thought that this is kind of relevant to our discussion today. In recent years, Bangladesh has reformed its approach to cyclone and flood risk management and preparedness, triggered by major loss of life and assets, notably during the cyclones of 1970 and 1991. The government of Bangladesh, civil society, and international development partners have demonstrated that investment in the systems and structures of flood risk management and cyclone preparedness saves lives, reduces economic loss, and protects development gains. As such, Bangladesh is cited often in the rationale for investment in disaster risk management activities globally. So Bangladesh has made significant gains and recognized gains in preparedness, essentially for cyclones. The design part, I don't know, it is explicitly included in that statement. Size and duration. So coming back to hurricanes or cyclones, the size and duration, the two things that we were talking about, that these huge storms cover a large geographic area and move very slowly. They sit there for a long time. Size and duration makes much higher probability of striking a given coastal location, unlike, again, tornadoes, localized in time and space. So the likelihood of a particular place being hit by a tornado is very low. Hurricanes are huge. They seem to stay there forever. And as a result, the chances of a community, coastal community, being hit by a cyclone are quite high. These cyclones control design wind speeds in cyclone-prone regions. No question, it's not thunderstorms anymore. The cyclones take over. Areas vulnerable to cyclones in Bangladesh, these areas include the Sundarbans, southern parts of Barishal and Patuakhali, Hatia, Bhola, eastern parts of Chittagong, and Cox's Bazar. I copied it from BNBC. I do not understand eastern parts of Chittagong. If you look at the map, I think it should be the western part of Chittagong. That is on the Bay of Bengal coast. You go to the east, it's mountains. So I don't quite understand that part. But anyway, it gives you an idea of where the problem is. Southern Bengal, and then the part Chittagong, Cox's Bazar. You know, I don't have to tell you. So this is the design wind speed map. We say design wind speed in the standard and BNBC. It is basic wind speed. The same thing, whichever way you like. I somehow never got to never learned to say basic wind speed. I don't know why. Uh, Anyhow, so the wind speeds are given on that on this map, and the cyclone prone areas are basically the areas in dark color on the map. Right? The coloring is not to indicate cyclone prone regions, but the coloring gives you a pretty good idea of cyclone prone regions. On this map, the lowest wind speed is 41.4 meters per second, and the highest is 80 meters per second here. So 41 to 80. 41 meters per second is 117 miles per hour, and 41, the lowest value, meters per second, is 93 miles per hour. If you compare with the ASCE 705 map for the United States, which uses the same basic wind speed, like the same definition of basic wind speed, you see most of the US has 90 miles per hour, which is very comparable, obviously, to 93. But the highest at the tip of Florida is 150 miles per hour. The 179 is significantly higher than that. And remember, always, pressure due to wind is proportional to the square of the velocity. So you go from 150 to 180, that is a sizable increase, but 150 squared to 180 squared is a much bigger increase. Okay, so I want you to appreciate that in parts of Bangladesh you have to design for extremely high design wind speeds, which will give you very high design forces to deal with in your structure. Special wind regions. The basic wind speed shall be increased where records or experience indicate that the wind speeds are higher than those reflected in the map that I just showed you. Mountainous terrain, gorges, and special regions shall be examined for unusual wind conditions. The authority having jurisdiction shall, if necessary, adjust the values given in the figure to account for higher local wind speeds. Such adjustment shall be based on adequate meteorological information and other necessary data. So where we have this potential problem, let's say Chittagong or Chittagong Hill Tracts, what should ideally happen is that the local jurisdiction, there is Chittagong Development Authority, and if within their region there are such areas, special wind regions, the most desirable scenario is that the authority will tell you what wind speeds to use for construction in those areas. If that doesn't happen, ASCE gives you advice or guidance that you should consult with somebody locally knowledgeable. It's not, it probably is not an expert from the US, but somebody that is knowledgeable about the wind in Chittagong Hill Tracts area. Okay, so somebody you consult is somebody locally knowledgeable. That's what ASCE 7 advises. Okay, let us now spend a little bit of time on this equation. So you have seen P, the wind pressure, is equal to Q, the velocity pressure, times G, the gust effect factor, times C sub P, the external pressure coefficient. The Q, the velocity pressure at a height Z above ground level. We say Z feet, here it is Z meters, I don't know. Anyway, so Q at a height Z above ground level is essentially, sorry, essentially 1/2 rho v squared. From this is from basic physics. 1/2 the density of the air multiplied by the wind velocity squared. The half the density of air in metric units, SI units, is this 00613. We have 00256 in ASC7. That's the number. I know this number is kind of strange to me, but anyway, that's a very important number, your number. Okay, 00613. That is half of rho times v squared. That's velocity pressure. That is very basic. Then we have a number of modification factors, which are all important. Okay? K sub z, K sub zt, K sub d, and I. Okay. Now in the equation, very importantly, the Q sub z is in kilonewton per square meter. V is in meters per second. That's you have to know that and always remember that. Okay. The wind provisions I mentioned at the beginning, BNBC wind provisions, are those of ASC 705. I will from time to time use ASC 705 section numbers and such. One place I have deliberately gone to ASC 710 because that is an important topic that was not covered in ASC 705. I'll indicate when the time comes. Okay, so 00613 was it the number? 00613 v squared, the basic wind speed squared, and then the K sub z, K sub zt, K sub d, and I. Okay. Let's look at each term individually. The basic wind speed, what is it? It is 3-second gust speed, and I will define that later. It's an wind velocity changes from one instant to the next. It is never constant over any significant period of time. So in design, we have no choice but to use some kind of an average wind velocity. 3-second gust speed uses 3 seconds as the averaging time. So this is wind speed averaged over 3 seconds. Now, when we say that, it is not just 1 3-second that you choose randomly. The agencies like NOAA, the National Oceanic and Atmospheric Administration, have well, they take wind speed average over 1 3-second period, then the next 3-second period, then the next 3-second period. This process goes on for a year or longer. And then they take the highest 3-second average as the 3-second gust speed. Okay. Bangladesh, the process that was gone through, I don't quite know, but it will be something similar. The Meteorological Survey of Bangladesh must have done something very similar. Okay. So 3-second gust speed. There are other averaging times that have been used in the past and are used in other parts of the world, like Australia has a different averaging time, but 3-second gust speed has been used in the US since ASC 798. 10 wind velocity changes from 0 at the surface of the earth to whatever values it increases as we go up. Okay. So you have to specify at which height above ground level you are looking at your velocity. So that distance is 10 meters. When we say basic wind speed, it is 3-second gust speed, and at 10 meters above the ground. And then the other thing we have to specify is the roughness of the ground. Is it smooth? Is it rough? Is it very rough? And that's where this exposure B comes in. Okay. There used to be exposures A, B, C, D. As you went from A to B to C to D, it became smoother and smoother. A was the roughest, centers of big cities and so forth. Then many years ago, exposure A was deleted from AC7. So since then, we have had B exposures B, C, and D. BNBC has renamed them A, B, and C. So what is B in AC7 is exposure A in BNBC. What is C in AC7 is B in BNBC, and what is D in AC7 is C in BNBC. That has caused me personally a lot of confusion. I find it very difficult to we are so used to, you know, exposure C being the default exposure and so forth, to kind of keep in mind that C is now B is kind of difficult. But as because of that, I have always kept the I have the AC7 designation crossed out, and then the BNBC designation underlined. So you know, at least I know what exposure we are talking about. Okay, so V is 3-second gas speed at 10 meters above ground of exposure B. That is essentially suburban exposure. Okay, it's neither very smooth nor very rough. And so, in addition to the three things, it is associated with a return period of 50 years. Okay, 50-year return period wind speed, as I said. So when you see the capital V in BNBC, it indicates all of that. It is 3-second gas speed at 10 meters above ground of exposure B, associated with a return period of 50 years. So that definition of basic wind speed, that it is at 10 meters above ground of exposure B, that tells you that we need to be able to modify it. We cannot do engineering if we are able to calculate wind speed only at 10 meters above ground of exposure B. What if we need wind speed at 20 meters above ground of exposure C? How do we do that? Okay, that's where K sub Z comes in. K sub Z takes us from the basic wind speed, which is at 10 meters above ground of exposure B, to wind speed at any height above ground of any exposure. It's the combined height and exposure coefficient. Okay, K sub Z, extremely important. And this is where the boundary layer effects come in. Atmospheric boundary layer is the layer of turbulent air in contact with Earth's surface. It is the first kilometer or so of the atmosphere. That's the atmospheric boundary layer, the first kilometer closest to the starting from the surface of the Earth. All buildings exist in this layer. We have not yet constructed a building more than a kilometer tall. Above this layer, wind speed is essentially constant with height. I don't know that it is constant, but essentially constant. Now, in the so the wind speed varies from 0 at the ground level and increases as we go up. How quickly it increases depends upon the roughness of the ground. What used to be exposure A of ASC 7 years ago, centers of large cities, gave us the steepest rise. BNBC exposure A, you have a fairly steep rise. B, it is flatter. C, wind coming over a large body of water, you have the flattest rise. Okay. The height of the atmospheric boundary layer, how thick it is, depends on the exposure category. For exposure, Bangladesh exposure C, the gradient height, as it is called, is 213 meters. For exposure B, it is 274 meters. And for exposure A, it is 357 meters. So the wind velocity for exposure C varies like this, and above a height of about 213 meters, it is essentially constant. It doesn't change all that terribly much. Now, the variation of wind speed with height and exposure is given, as I mentioned, by the K sub z factor. It is given by this expression. K sub z is equal to that. Z is any height above ground level. Z sub g is the gradient height that I just talked about. Depends on exposure category. For exposure C, Z sub g, the gradient height is 213 meters, Z sub g, and alpha is the power law exponent for each exposure category. That is given in the standard, equal to 7, 9.5, and 11.5 for exposures A, B, and C respectively. These are Bangladesh exposures A, B, and C. So if we know our exposure category, we immediately know Z sub g and alpha, and then we have K sub z. We can calculate wind velocity at any height above ground of any exposure. The next constant is K sub z t. That deals with what this picture is trying to depict. Okay? For a structure sited on flat ground, this would be the distribution of wind pressure along the height. But if the structure is sited on the upper half of a hill or an escarpment, as they're called, upper half of a hill, then the pressure distribution changes as shown in this picture. Okay, this would have been more characteristic of something on flat ground, on like below the hill, and on the hill the pressure distribution looks like this. We have to account for this fact for structures located on the upper half of a hill, and that is done through the K sub z t factor. Of all the factors, that is kind of the most complicated. I will show you the details, but I probably will not have time to go into the details. K sub d, I discussed with you yesterday. K sub d deals with the fact that at any location, if you keep records for a good length of time, you will see that there are predominant wind directions. At whatever locations, they say the northwest wind and the southwest wind are both very strong. Any other direction, wind is weaker. Now, when we are designing a building, we are not probably going to design for the northwest wind because, as I mentioned yesterday, wind direction, like velocity, changes from one instant to the next. So wind can be along the northwest direction instantaneously, but the very next instant the wind direction will have changed and it will no longer be along that most critical direction. So the directionality factor was devised to take this into account. It is 0.85 for all buildings. And this was introduced in ASC 798. So wind pressure was reduced 15% from ASC 795 to ASC 798. In order not to design for lower wind pressures, lower factored wind pressures than by ASC 795, the wind load factor was adjusted. In ASC 795, it was 1.3. Now the 1.3 was divided by the directionality factor of 0.85 because wind had been multiplied by it. 1.3 divided by 0.85 was 1.53. It was rounded up to 1.6. I told you the entire story yesterday. Okay. So the introduction of K sub D in the equation for Q was accompanied by the increase, the increase in the wind load factor in the strength design load combination from 1.3 to 1.6. Okay. Now the return period that I have been mentioning, that we design structures for 50-year return period. The return period is also known as mean recurrence interval. That is neither here nor there, just so that you know, because you see that term quite often. Used for statistical determination of the predicted wind speed. Now, return period of 50 years is used for ASC 7 design adopted by BNBC for normal use structures, office buildings, apartments, things of that kind. From the beginning of the of modern wind design that dates back to ASC 772, we have used a 100-year return period wind for important structures like hospitals, fire stations, police stations, things like that. Okay. Those are designed for higher wind speeds corresponding to a higher return period, a storm that can come once in 100 years, something. It is not quite accurate, but anyway, that probably is more relatable. How do I want to characterize it? Unimportant buildings like farm sheds where no life safety is at stake are allowed by ASC 7 to be designed for a 25-year return period. Okay? So normal buildings, standard use buildings, 50-year return period, important buildings, 100-year return period, unimportant buildings, 25-year return period. Does that require 3 sets of maps? 50-year return period map, 25-year return period map, 100-year return period map. Back then, the answer was no. When I say back then, from 1972 through 2005, the answer was no. We don't need 3 maps. That changed in ASC 7N. But again, we won't go there. Okay. So the return period is adjusted by using an importance factor I. We have one map, 50-year return period wind speed map. Then if we need 100-year return period wind speed, we multiply the 50-year return period wind by a factor of 1.15. Okay. So this can be done because the ratio between 100-year return period wind and 50-year return period wind is remarkably constant throughout the United States, outside of the hurricane-prone regions. Hurricane-prone regions are typically a different story. Okay. The conversion to 25-year return period wind is also done using an importance factor lower than 1. Okay, 0.87, 0.77. You'll see the details later. But this is the idea of the importance factor. I changes the return period on the wind speed. And I larger than 1 takes us to return period larger than 50 years, and I smaller than 1 takes us to return period smaller than 50 years. Okay, so by now we have taken a look at all the components of the velocity pressure Q. Now we come to the wind pressure P, which is Q times G times C sub P. Okay. Now we will discuss the gust factor G. That factor has to do with rapid fluctuation of wind. That's what gust is, a rapid fluctuation. Ordinary structures are sensitive to peak gusts of about 1 second duration. This is something we have learned from a lot of experience. Ordinary structures are sensitive to peak gusts of about 1 second duration. Flexible structures are more sensitive, rigid structures are less sensitive. Use of fastest mile wind in design is inadequate. So before we switch to 3-second gust speed in AC 798, the design basis in the United States was fastest mile wind speed. Back then, the averaging time, when we use fastest mile wind speed, the averaging time varies between 30 and 60 seconds. You should compare that to 3 seconds for the 3-second gust speed. So it was a much longer averaging time. The shorter the averaging time, the higher the average wind speed. So when the averaging time was that long, 30 to 60 seconds, the average wind speed was lower. I told you a short time ago, in AC 705, most of the United States has basic wind speed of 90 miles per hour. That number back then, when we used to use fastest mile wind speed, was 70 miles per hour, to give you an idea. Okay. Now, the thing is, if a building is sensitive to 1 second gust, you cannot design it for wind averaged over 30 to 60 seconds and leave it at that. That would be terribly unconservative. So we have to bring the average wind speed up by multiplying with a gust effect factor. Now the point is that gust effect factor could be applied to the velocity, bringing the velocity up, or it can be applied to the pressure due to wind, bringing the pressure up. If we want to apply the gust effect factor to the pressure due to wind, the factor would be the square of the factor that we would have applied to velocity, because pressure is proportional to the square of the velocity. So if we apply the gust effect factor to the wind velocity, it would have been a smaller factor. AC7 chose long years ago to apply the gust effect factor to the pressure due to wind. So we have a larger gust effect factor. Okay. So anyway, so to cut a long story short, when we used to use fastest mile wind speed as the basis of design, we had to use a gust effect factor larger than 1 to bring the wind pressure up. When we switch to 3-second gust speed as the basis of design, that changed. Now, many buildings, the vast majority of buildings are low rise, at least in the US. Okay, 5 stories or lower, 95 to 97%, I don't know. Vast majority of buildings, and those are not sensitive even to 3-second gust. Okay. So for those buildings, we are allowed to use a gust effect factor of 0.885. So we bring the 3-second gust speed actually down. And then for the more flexible buildings, we calculate the gust effect factor, which typically comes out above 1, but doesn't have to. So it has changed. But the idea of the gust effect factor is still valid, that we go from the averaging time to the gust duration to which a building is sensitive. Okay. So gust effect factor accounts for the loading effects in the along wind direction due to wind turbulence structure interaction. That's what it is. We are accounting for wind turbulence structure interaction in the direction of wind. Also accounts for along wind loading effects due to dynamic amplification for flexible structures. As I say, flexible structures are more sensitive. The gust effect factor does not account for other dynamic effects such as across wind loads. Across wind effects are not accounted for through the gust effect factor. Okay. The concept of average wind velocity, averaging time, let's look at that in just a little bit of detail. So instantaneous velocity of wind at a point as a function of time looks like this. Okay. As I said, it is not constant from one instant to the next, it changes. So we have to use some kind of an average in design. Maximum wind speed averaged over, so when we used to use fastest mile wind speed, the averaging time was the time it took a mile of wind, a mile long, what's the word? The time it took for a mile length of wind to pass through the measuring instrument called the anemometer. So the time it took for 1 mile of wind to pass through the measuring instrument. If the wind speed was 60 miles per hour, that time was 60 seconds, 3,600 seconds in an hour divided by 60 miles per hour. 60 seconds is the time a mile of wind would take to go through the instrument. If the wind speed was 120 miles per hour, it would take the wind a mile of wind only 30 seconds to go through the instrument. And since wind velocity is typically in that range of 60 to 120 miles per hour, our averaging time was between 30 and 60 seconds. In AC7, I kept on saying 98. This switch was made in 95. Yeah. The switch to 3-second gust speed. So in AC 795 onwards, we have used 3-second gust speed as the basis of design. The averaging time is down from the variable 30 to 60 seconds to a fixed 3 seconds. Okay. That's what we have used since 95 for a long time. Fastest mile wind speed people generally have forgotten. Now this slide tells you what I told you already, that the shorter the averaging time, the higher the average wind speed. On this slide, on the x-axis is the averaging time, t. On the y-axis, it is the wind speed averaged over t seconds divided by wind speed averaged over an hour, 3,600 seconds. Okay. So this figure tells you 1 second gust speed is 155% of 1 hour wind speed averaged over 1 hour, 155% of that. Okay, the averaging time goes down from an hour to 1 second. The average wind speed goes up by 55%. 3 second gust speed, this is 1, 2, 3. 3 second gust speed is something like 150% of hourly wind speed. Okay, so that gives you a little bit of a feel about what we are dealing with. Now, gust effect factor. Starting with AC 795, again I said 98, but 95 is when we switch to 3 second gust speed. So 95. Starting with when we adopted 3 second gust speed as the basis of design, G, as I told you, may be taken as 0.85 for all rigid buildings, and rigid versus flexible I will define fairly soon. G must be calculated for flexible buildings. This calculation is a major pain. There are, I think, 13 equations involved. The equations get uglier as you go. And I once did it by hand just to see how much trouble it was. And it took me an hour and a half of hard labor to calculate that one number. And I still remember after the hour and a half, my number was 0.87. So I had a flexible building by definition of AC 7, had to calculate gust effect factor, calculated it, and felt, I don't know, felt pretty terrible that hour and a half of labor had taken me from a gust effect factor of 0.85 to 0.87. So something is not quite right about the calculation of gust effect factor, but we have had the same thing for years and years. No discussion of any change. I have seen that when you calculate gust effect factor less than 1 is not that terribly uncommon. I don't know enough to tell you why. They definitely are sometimes larger than 1, as you would expect. But if you calculate gust effect factors of 2, 3, 4 numbers like that, then AC 7 tells you in the commentary, you should go for, you should abandon this analytical approach and go for either sophisticated wind analysis, which basically cannot be done, or wind tunnel testing. So keep that in mind. Okay. G is included in it. So for low-rise flexible buildings, and I will define flexible buildings, I'll define low-rise. For low-rise flexible buildings, there is a slightly different or specialized design approach. And in that, G and C sub P are lumped together and given to us in a lumped together fashion. We do not have separate G and C sub P values given. Okay, so rigid versus flexible. In very simple terms, we all understand, I think, period. All engineers understand period. Period is the time it takes for a body, let's say pendulum. Okay, you swing the pendulum. The time it takes for it to go from a position of rest to an extreme position to the right to an extreme position to the left and come back to rest. That time is the period. Okay. So when a body is given a disturbance, when it is disturbed, there is a better word that doesn't come to me. Anyway, the time it takes for it to go from a position of rest to an extreme position to the right, to an extreme position to the left and come back to rest is the period. Now, when the period of a structure is less than or equal to 1 second, it is a rigid building or structure. Okay, less than or 1 second is rigid. When the period is more than 1 second, it is a flexible structure. Now there are details involved, unfortunately. A structure, except for very simple ones, one-story rigid box, has not just one period but multiple periods. We talk about modes of vibration, that is fundamental mode, second mode, third mode, etc. So here, when we are defining rigid versus flexible buildings, we use the period of the first mode, the fundamental mode. This is why you see T sub 1. Okay? And then to make things more complicated for engineers, wind people are scientists, not engineers, people who deal with wind. And scientists somehow do not, unlike engineers, do not talk about period. Their thing is frequency. Frequency is the reciprocal of period. Okay, so period is in seconds, t second. If you take the reciprocal of that, 1 over t second to the power minus 1, the 1 over t would be the frequency. Okay, that we used to denote it by F in ASC7. It is N. I don't know why. And so reciprocal of t sub 1 would be N sub 1, the frequency of the first mode. The unit of that would be second to the power minus 1. And second to the power minus 1 is called hertz. Okay, so when we say period less than or equal to 1 second, they will say fundamental frequency larger than or equal to 1 hertz, which for me, it's complicated, but that's how the wind provisions are written. Okay, a flexible building has period, fundamental period exceeding 1 second, which means fundamental frequency less than 1 hertz. Okay, so that is the definition of rigid versus flexible. Please remember the way I said it first. A structure with a fundamental period T sub 1 larger than or equal to 1 second is a flexible building. If it is smaller than 1 second, then it is a rigid building. Okay? So I probably the equal sign, I probably put it in the wrong place. So when the period is less than or equal to 1 second, it is a rigid building. When it is larger than 1 second, it's a flexible building. Don't go to frequency would be my advice. Or if you see frequency, take the reciprocal and then you'll be oriented. I always feel oriented when I have gone from frequency to period. Okay? So for a long time, ASC7 did not tell you how to calculate this frequency. That is the basis of distinction between rigid and flexible buildings. ASC705 put some expressions in the commentary. And then in ASC710, some of those expressions moved into the main body of the code. So this is the only time I have invoked ASC 710. ASC 705 is the basis of BNBC 2020, but ASC 705 does not have expressions for expressions by which you can calculate frequency. So I have decided to show you that ASC 710 tells you how to calculate approximate frequency. Okay, so instead of calculating n sub 1 by eigenvalue analysis, as we call it, by sophisticated analysis on the computer, you are allowed to calculate an approximate frequency n sub a by using formulas that are given in ASC 710. Okay. So as an alternative to performing an analysis to determine n sub 1, the approximate building natural frequency n sub a shall be permitted to be calculated in accordance with section such and such. Now, in order for you to be able to use the approximate formulas, you have to meet two requirements. One is the building has to be less than or equal to 91 meters in height. That would be about 300 feet, I think. So that is not too much of a limitation, because taller buildings we will do sophisticated analysis anyway. So, and the other limitation is building height is less than 4 times its effective length. Okay. So building height is less than its effective length. We are trying to exclude the very flexible building from this calculation of approximate frequency. So a building taller than 91 meters is judged to be flexible, and a building with height to effective length ratio larger than 1 is also thought to be flexible. Now, this is where I always have problem with the wind chapter. For years and years, and it was in ASC 705 also, there was something said in the commentary that if the height to minimum plan dimension ratio of a building is 4 or larger, it is a flexible building. It's a rule of thumb. Now, instead of saying that, that was pretty simple, minimum plan dimension. Instead of that, they have come up with this effective length. So you take the length, L is always the plan dimension parallel to wind, and perpendicular to wind plan dimension is B. Remember that always in ASC 7 wind provisions, capital L is plan dimension parallel to wind, and B is plan dimension perpendicular to wind. So you take plan dimension parallel to wind at level I, you take the multiply that by the height to level I, you multiply over all, you sum over all the stories in the building, you divide that by the sum of heights to the various levels. So you are basically calculating an average plan dimension parallel to wind over the height of the building. I don't know why that complication was necessary. We could just say, building height to minimum plan dimension ratio, something like that. Anyhow, so if those limitations are satisfied, then you can calculate the approximate natural frequency by these formulas, where H is the mean roof height, as it is called, height to the halfway point between eave and ridge. And again, H will be very rigorously defined on a subsequent slide, but H is always in ASC 7 wind provisions the mean roof height. If it is a flat roof, it is the height to the roof. There is a more complicated formula for shear wall buildings. This formula is a little bit problematic, and I included it because it is an SC 705, but my advice would be don't try to use that formula. And I don't want to spend time on that. Okay. A little more basic stuff before we go into the wind design methods. There are three methods of wind design in SC 705: method 1, method 2, method 3, as you will see. But I don't feel that we should go there before fully understanding the basics that we are dealing with. So this is wind flow around a building. As I said, any building that you put up stands in the way of wind. So the wind has no choice but to hit the building and to go around the building. Okay. So on this is called the windward face of the building. This is so the direction of wind, as you see, is from left to right. This is the windward face. This is the leeward face, and this is the windward roof. This is the leeward roof, and the other two faces are the side faces. This is the terminology we typically use. Okay. On the windward face, the wind pressure is positive, meaning it is above ambient. Ambient pressure is the pressure that would have existed if the building were not there. When we put up the building on the windward face of the building, we have positive pressure above ambient. Okay. Everywhere else, on the leeward face, on the side faces, on the roof, we have suction, we have negative pressure. We have pressure below ambient. That is something you have to you need to understand. On the leeward roof, we can have pressure rather than suction. If it is a long leeward roof, then it is possible that after a while you will have pressure on the leeward roof. But most of the time, except on the windward face, we will have suction on all the other faces, including windward roof and leeward roof. And this is shown in this picture. This is schematic, but a very good picture. Okay. So this is the pressure variation on the windward face. This is suction on the windward roof. This is suction on the leeward roof. This is suction on the leeward face. The suctions on the side faces are not shown in the picture. Near the center of the windward face, there is a point called stagnation point where the pressure due to wind is the highest of any point on the surface of the building. And that pressure is called the stagnation pressure. Okay. So note this: for many practical geometries that are built, in the US, I think most of you probably know, most residential construction is wood and the roofs are pitched roofs. Okay. A building looks really like that, residential buildings. And at that corner, look at the suction. Huge suctions develop at that corner of the windward face and the windward roof. And unless the roof is held down sufficiently, the roof is sucked up by the wind. And when that happens, the wall doesn't have lateral support. It comes down. This is the mode of failure that we have seen in after every serious wind event. And so the basic points that I'm trying to make is that the roof has to be held down to the building, and very importantly, the building has to be held down to the foundation. That I have found missing. After hurricanes, I really with my own eyes have seen whole buildings uprooted from where, sucked up from where it was, and deposited, several, a couple 100 years away. That's because the anchor bolts are flimsy or non-existent. The bolts that anchored the building to the foundation. Now, in concrete construction, none of this can happen, obviously. You don't have, a wood structure anchored to a foundation. But still, I mean, there are non-building structures, there are tanks, there are things that are attached by anchor bolts, and you have to be aware of this huge suction that wind imposes. Okay, this is kind of physics, if you like. The pressure due to wind, not pressure due to wind, the stagnation pressure that I was talking about is ambient pressure plus rho v squared by 2, rho being the air density, kilogram second square by meter cube, meter to the power. The units you will have to figure out because it is metric. I prefer not to go there. Okay, the pressure above ambient, which is P sub S prime in this on this slide, is then rho v squared over 2. Okay, the pressure coefficient C sub P that we are talking about is pressure above ambient P prime divided by half rho v squared. Okay, so when we say pressure coefficient, that's what we mean. Pressure at any point. This P prime is what we typically refer to as pressure, wind pressure, pressure above ambient. So it is wind pressure at any point divided by the stagnation pressure, 1/2 rho v squared. So at the stagnation point, it is equal to 1. As you move away from the stagnation point on the windward face, the numbers decrease as shown in the picture. Okay. On the leeward face, it is suction. You look at the numbers. On the side faces, it is suction. You look at the numbers. On the roof, it is a flat roof. It is suction, and you again look at the numbers. This very simple picture gives you a very, very good idea of what happens to a building when wind blows on it. Okay, on the windward face, we have pressure. On every other face, we have suction. The pressure varies as shown in the picture. And I will tell you, as complicated and sophisticated our wind design is, we still do not account for this point-by-point variation of wind. The entire windward face is designed for a C sub P of plus 0.8, one value. Okay, that's where we are at, as you will see on subsequent slides. Okay. So we are back to the basic equation. P is equal to Q G C sub P, except we know quite a bit about the terms now. We discussed Q early on. We discussed G. We now discuss C sub P. Okay. The next thing, maybe this is a good time for a break, like yesterday about this. Yeah. So 24. So 29 after, in 5 minutes, if you please come back, I'll start 29 after the hour. Okay. Thank you. Okay, I think it is time. So we talked about variation of wind pressure on a face of a building. We are now looking at wind pressures on a building. The main point that I need to make here, or would like to make here, is that the velocity of wind, as we have discussed, varies with height above ground level. So pressure due to wind also varies or increases with height above ground level. That basic fact we recognize only on the windward face of our building. On all the other faces, the leeward face, the side faces, the roofs, we go for a constant suction evaluated at the mean roof height level. So the leeward face is designed for a constant suction that is evaluated at the mean roof height level, the height to the point halfway between the eave and the ridge. The leeward roof is designed for suction evaluated at the mean roof height level. The windward roof, which under certain circumstances can be under pressure rather than suction, be that as it may, will be designed for pressure or suction evaluated at the mean roof height level. It will be constant. On the side faces also, it is constant suction evaluated at the mean roof height level. So this is our level of sophistication even today, just so that you appreciate it. Okay. Then we go, so far we have been talking about external pressure on our building. There are circumstances when we have to, so when we are designing an entire building, that is typically our concern, the external pressure due to wind. However, if we are designing a component of a building, the walls or the roof, we need to consider the pressure inside our building. Okay, so this is now the topic. So the first picture shows a structure for illustration. We are drawing a structure that is made of tent-like material, so it inflates or deflates as wind gets in or out. So in the first picture, we have an opening only on the windward face, so that wind gets in but has no way of getting out. Then we will have positive internal pressure above ambient. In the second picture, the only openings are suction openings on the, in this case, on the leeward face. There are many suction faces, the side faces, the leeward face, the roof. So in this case, in the picture, we have the only opening on the leeward face. It is a suction opening. So wind gets out, has no way of getting in. So we have negative internal pressure. In the third picture, the only opening is on the side face. The side face is a suction face. So again, we have negative internal pressure. So we can have positive internal pressure, we can have negative internal pressure. In design, invariably, we always consider both possibilities, both internal positive pressure and external positive pressure. Okay. That brings us to something extremely important that you absolutely need to understand. When I say understand, not just by your head, but you have to instinctively understand. When somebody tells you an open building or a partially closed enclosed building, okay. So anyway, there is a 3-tier enclosure classification. A building can be open, partially enclosed, or enclosed. Okay, open, partially enclosed, or enclosed. An open building, and please listen to me very closely. The slides I will probably not quite use. I don't know. At least I will not read the slides for this segment. So please listen to me. This is extremely important. So an open building is a building that has at least 80% of each face physically open. at least 80% of each face physically open. That is pretty unambiguous. I have never met anybody confused about what an open building means by ASCE definition. And it is typically, I don't have that picture here. Okay, it is typically not a building. I have a picture later on. You will see an open building. It is typically a roof over a few columns, a shade of some kind. Okay? So at least 80% of each face basically open. Then partially enclosed building. A partially enclosed building has windward openings. It has suction openings, but windward openings predominate, so that more wind gets in than can get out, so that we have positive internal pressure build up. That is a partially enclosed building. I will repeat. It has windward openings, it has suction openings, but windward openings predominate, so that more wind gets in than can get out, so we have positive pressure buildup. If a building is not partially open by this definition, then the only two possibilities are that it is open or enclosed. Open building, we have seen, is a building that has 80% of each face basically open. So if a building is not partially enclosed by the definition I just gave you, and if it does not have 80% of each face physically open, then it is an enclosed building. By this definition, most buildings we design come out to be enclosed. The parking structures that we see with all the openings that we are familiar with turn out to be enclosed buildings by ASCE 7 definition. So when we say enclosed building in ASCE 7 wind design provisions, it does not mean a jailhouse without openings on all the faces. It simply means it is a building that does not meet the definitions for an enclosed building, or a partially enclosed building, or an open building. Okay? So an enclosed building is defined by default. It is not directly defined. So that's as I said, extremely important. I think this is the best way I know how to define, and the technical definitions you will see later. There are technical definitions that translate what I tried to describe for you. Okay. So for buildings with external and internal pressure, the pressure due to wind P is QGC sub P, the external pressure term that we have seen, minus internal pressure QIGC sub PI. Q sub I is velocity pressure calculated for internal pressure. Most applications we take Q sub I equal to Q sub H, the velocity pressure evaluated at the mean roof height level. You have to read up ASCE 7, that is not always permitted, but most applications that's what we do, Q sub I equal to Q sub H. And remember, G times C sub Pi is taken positive as well as negative. So in this picture, the internal pressure is positive. It is going towards the surfaces. So on the roof, we have suction and we have internal pressure. So the net of the two, the external pressure minus the internal pressure, is suction of 1.8. Okay. The internal pressure adds to the external suction. If we are designing this roof, then that's what we have to design for. The 1.8 suction. This is negative internal pressure. Now the net is 1.2 plus 0.3, which is negative 0.9. So this is not the more critical case. But as far as this wall goes, this is more critical. This is plus 7. This is negative 3. So the net is 1.0. Negative pressure gives you 1.0. Positive pressure gave you a net of 0.1. So in this case, anyway, the two pictures are pretty graphic. You will see how the external pressure minus internal pressure, what that comes to, depending upon the direction of internal pressure. Now, there is throughout ASCE 7 BNBC distinction between main wind force resisting system and components and cladding. This is a huge distinction, and there is definition of component and cladding, but basically in very basic terms, components are directly loaded by the wind. The main wind force resisting system derives its loading from components and cladding. That's the main distinction. Components are directly loaded. The main wind force resisting system derives its loading from the components and the cladding. There are times, like a roof truss, when we are not sure it's a component or part of the main wind force resisting system. In those cases, the best advice is treat it as a component, treat it as a main wind force resisting system. Whichever way you get higher wind pressures to design for is the way to go. Okay, so now for components and cladding, the pressure coefficients that we are given in ASCE 7 are area-based values. They consider, you will see, it will be apparent as I go. For component and cladding elements, the effective area, this is very important in dealing with components and cladding. There is something called effective area defined, which is equal to the span length, okay, like this purlin. We'll take the span length, multiply that by an effective width that need not be any less than 1/3 the span length. This is how it has always been phrased. Need not be less than 1/3 the span length. So effective area is like tributary area, but not quite the same. It is the span length multiplied by an effective width that need not be taken any less than 1/3 the span length. Okay. The larger the effective area, the lower the pressure on component and cladding. When I say pressure, it includes suction. It's typically suction. Okay. For cladding fasteners, effective area is the tributary area of the fastener. That's kind of important. Okay. A bolt or a screw, when you design those, the effective area is the tributary area. Then BNBC, as in ASCE 7, has minimum design wind loading. No matter what you calculate, these are additional load cases. Okay, so on the vertical projection of the wall, it is 10 pounds per square foot, which is half a kilonewton per square meter. And in the longitudinal direction, it is also 10 pounds per square foot on the face. That the pictures are pretty graphic. Now, the idea here is not So we have a pressure distribution that we have calculated. We are not saying if you calculate values less than 10 pounds per square foot, make it equal to 10 pounds per square foot. No, you don't tamper with what you have calculated. You design your building for that distribution and also this distribution. This is like an additional load case. Okay, that is what I just said is quite important. But these minimum design wind loads, there are times when they govern. Okay, ASC 7 definition of basic wind speed. They did away with the 50-year return period on the wind in ASC 705. They opted for the committee, ASC 7 committee, pointed out that when you, so loads calculated from the design wind speed map, okay, we get the speed from the map, square of that multiplied by other things gives us pressure. Pressure translates into load. When that load is factored up by the wind load factor, which today is 1.6, that factor load has a return period on it of 500 years. So instead of saying 50-year return period wind speed, ASC 705 chose to tell you that the factor load that we are designing for under ASC 705 had a 500-year return period on it. Okay, so this is nuance. This is another way of looking at it, but this is what they chose to do. On the hurricane coastline, to maintain the 500-year return period on the factor load, the return period on the wind speed had to be higher than 50 years. And that was done. And this is what is being described in the last line. Map contours include hurricane importance factor. It probably is not said the best way, but that's what it means. Okay. So the 500-year return period on the factor loads was maintained even on the hurricane coastline. Okay, definitions. Time is I knew would be a problem. It's probably a bigger problem than I thought. I don't know. I don't have a vivid recollection of how many slides are left or anything like that. So anyway, simple diaphragm building I will define with a picture just a little bit later. So let us not spend time on it. Impact resistant glazing. Glazing that has been shown by testing or other approved, okay, to withstand the impact of wind-borne missiles likely to be generated in wind-borne debris region during design winds. Wind-borne debris region I haven't defined yet, but I will very soon. So there is hurricane-prone region or cyclone-prone region. A part of that is designated as wind-borne debris region. Every structure in wind-borne debris region must have the glazing, the glass, either impact resistant, the glass itself has to be impact resistant, or there has to be impact resistant covering on the glass. Okay? So there is a small missile test and a large missile test that the glass has to undergo before it can be sold to you. Okay? So impact resistant glazing, glass that will remain intact upon impact from small missiles and large missiles. I think that's probably enough of a description. Hurricane-prone region or cyclone-prone region, areas vulnerable to cyclones. Okay, that is the BNBC definition. In Bangladesh, these areas include the Sundarbans. You have seen this before, southern parts of Borishal and Patuakhali, Hatia, Bhola, eastern parts of Chittagong and Cox's Bazar. Impact resistant covering, like impact resistant glazing, has to withstand the impact of small and large missiles. Main roof height, H, is the average of the, okay, I have a picture. So main roof height, as I kept on saying, is the height to the halfway point between the eave and the ridge, which will make it equal to the average of A and B. Okay? But there is a major twist to it. If the roof angle is less than or equal to 10 degrees, which is quite often the case, we take the eave height as the mean roof height. Okay, so that is something you have to catch on to in AC7 design. For flattish roofs, theta less than or equal to 10 degrees, the eave height is taken as the mean roof height. Opening, this is extremely important definition. I cannot overemphasize this. Apertures or holes in the building envelope which allow air to flow through the building envelope, and which are, this is the important part, which are designed as open during design winds as defined by these provisions. So an opening, let's take a door or a window. Is it an operable door or a window? Is it an opening or is it an enclosure? So this is saying that an operable window is an opening if it is going to remain open in the design wind event. And AC7, or I don't know where, but the way it is practiced, I can assure you, is an operable, well, windows we always assume open, openings. There is no question in design. The doors we also take as openings unless there is a crew in place, instructions in place, making sure that the door will in fact be closed at the approach of a store. So this becomes very important. You take a hangar or a automobile repair shop, though those roll down doors, those are huge openings. If they're treated as openings, can change the enclosure classification of the building. Are they openings? Are they enclosures? So you have to treat them as openings unless there is a crew in place and instructions in place to make sure that a roll down door will in fact be closed at the approach of a store. Okay, otherwise they're openings. Windborne debris region. Okay, so areas within cyclone prone region, that is the first thing, located where the the design wind speed is more than 200 kilometers per hour, or if you're within 1 mile of the coast, then 180 kilometers per hour will put you in a windborne debris region. So windborne debris region is a part of the hurricane prone region where the design wind speed is 200 kilometers per hour or more, or if you're within 1 mile of the coast, then 180 kilometers per hour or more will put you in a windborne debris region where the glazing on your structure has to be impact resistant. Okay. Then I think this is probably the last big problematic area that is not easy to understand. The exposure categories. we have B, C, and D. Anyway, let us look at this. So exposure categories, let me skip the writing. AC7 is now telling you that if the direction of wind is from bottom to top in the picture, I'm sorry, then you will consider segments 1 and 8 and look at the roughness of the terrain, and whichever segment gives you has the rougher terrain will give you the roughness category, not the exposure category for that direction of wind. If the direction of wind changes from up to down, then this will be the upwind direction. Then you will look at segments 4 and 5, and whichever has the rougher terrain will give you the roughness category for that face of the building or that direction of wind. Okay. So we have defined in BNBC AC7 roughness categories. In AC7 they are B, C, and D. In BNBC they are A, B, and C. Okay. So roughness category A is urban and suburban areas, wooded areas, or other terrain with numerous closely spaced obstructions having the size of single family dwellings or larger. So this is very basic and important. Your surface roughness A is urban and suburban areas, wooded areas, or other terrain with numerous closely spaced obstructions having the size of single family dwellings or larger. Now, this is an American definition, single family dwelling in Bangladesh. What it would mean, I don't exactly know. But anyway, if you read this and the AC7 commentary, you will have a pretty good feel. B is open terrain with scattered obstructions having heights generally less than 9.1 meters, that would be 30 feet. This category includes flat open country, grasslands, and all water surfaces in hurricane-prone regions. Okay, so B is flat open country. Category A is suburban. B is flat open country, grasslands, and wind coming over the water in cyclone-prone regions. Okay, that again has explanation, but I do not have time to go into that level of detail. C is flat, unobstructed areas and water surfaces outside cyclone-prone regions. Okay, so cyclone-prone regions you cannot have exposure, the roughness category C. The worst is B. Okay. When water is coming, when wind is coming over a large body of water that is not in a cyclone-prone region, then you have surface roughness C. This category includes smooth, mud flats, and salt flats, if you have any. Okay, so we have roughness categories A, B, and C. Then exposure categories A, B, and C are defined in terms of those roughness categories and upwind distance. So exposure category A shall apply where surface roughness A prevails in the upwind direction for at least 792 meters or 20 times the building height, whichever is greater. Okay. There is exception. But the point is that exposure category is defined in terms of roughness category and upwind distance over which that roughness category has to prevail. Exposure B is anything that is not exposure A or C. Exposure B is defined by default. That's the default exposure category, very important. Exposure C in a way is pretty messed up. So exposure C shall apply where surface roughness C prevails in the upwind direction for at least 1524 meters or 20 times the building height, whichever is greater. Up to that, there is no problem. This is how A was defined. Okay? So you have surface roughness C for a certain distance in the upwind direction, always upwind. Then it says, this is the confusing part, exposure C shall extend into downwind areas of surface roughness A or B for a distance of 200 meters or 20 times the building height, whichever is greater. So now it talks about extending downwind, and it is very, very confusing. So we got questions. So what downwind area? Let me skip this. So we found in 2009 IBC much better language. 2009 IBC made that sentence, the AC7 sentence that talked about downwind distance. 2009 IBC made that sentence more easily understood. The 2009 IBC did not use the term downwind areas and did not make reference to surface roughness A or B, but simply reads exposure C shall extend inland from the shoreline for a distance of 200 meters or 20 times the height of the building, whichever is greater. And this we have shown in a picture. So first of all, it has to be a large enough body of water. The X distance has to be no smaller than 1524 meters and 20 times the building height. So you can have exposure C only on, now ocean is excluded. Remember, ocean is not excluded. The cyclone prone region was excluded. So it has to be calm ocean. Anyway, the point I'm trying to make is that on a river, if your site is on a river, you probably will not have exposure C. It is not a large enough body of water. The body of water has to have this minimum extent of 1524 meters or 20 times the building height. And then exposure C shall extend inland by a distance no larger than 200 meters or 20 times the building height. Okay, so all of anyway, what I said is important. First of all, this has to have a minimum extent, and then the exposure C extends inland for a considerable distance. This is something you have to appreciate and understand. Like, quite a few situations, this turns out to be quite important. Another very good question we got: why does exposure C extend so far inland, and why is it dependent on the height of the structure? This is the answer. After a change in surface roughness, wind has to travel a sufficient distance over the new terrain for the velocity or pressure distribution to attain a new changed equilibrium state over a certain height above ground level. The required travel distance is a function of that height. So you can read that at your leisure and you will probably have a deeper understanding. For a site located in, this I'll let you read. Okay. So in AC7, I don't remember until which edition, there used to be these pictures of exposure A that has now been deleted. This is exposure B, Bangladesh exposure A, suburban exposure. I think the pictures are still very helpful. Now they are gone. I don't think they're in there. This is suburban exposure A. This is urban exposure A. Remember, the previous A has been deleted. So urban, the center of large city, is now also exposure B or your exposure A. So this is suburban exposure A. This is urban exposure A. This is so this has exposure A and exposure B. Exposure B is flat open country in the same picture. This is exposure B, flat open country. This distance I will not go into, that's a detail. And this is exposure C. This is Duluth, Minnesota, sitting on one of the Great Lakes. This is Lake Superior. And it's a huge body of water. So when water comes from this direction over the water, you have exposure C. Okay, that brings us to the design methods. And I have less than a half hour, so I do not exactly know. I kind of anticipated this, but I didn't come to any solution. Anyhow,
you have 60 slides more left after this.
Yeah, I understand.
Yeah, you can continue.
Yeah, I
Yeah.
probably better continue. Somehow I thought of skipping the simplified procedure. Do not feel quite right. Let's try to get through and see what happens to the time. And maybe we'll stay after 11 for a little bit to answer questions. I don't know. So this method one, so-called simplified procedure of BNBC, is based on the low-rise analytical procedure, as we call it. And that is also in ASC 7 BNBC. And you will see very distinct similarities between the two. Applies loads on projected areas as opposed to perpendicular to the roof. You know, if it is a pitched roof, the loads are applied on projected areas, restricted to the simplified procedure is restricted to low-rise buildings as defined in ASC 7 or BNBC, simple diaphragm buildings. Simple diaphragm building, I showed you a definition before. This is in words also. Let me cut to through the chase and tell you exactly what a simple diaphragm building is. So this is a building where wind acts on the let us say this cladding panel of the building, okay, or on this, yeah, cladding panel is probably the best, yeah. So wind acts on this cladding panel, and the cladding panel bending between supports provided by this diaphragm and that diaphragm, the diaphragms at the two levels, transfers the wind to the diaphragms, okay. So shear forces are, so that phase of the diaphragm goes into compression, that phase of the diaphragm goes into tension. There is in-plane bending of the diaphragm like that, okay, and shear forces develop along faces of the diaphragm parallel to the wind. Those shears are transferred to the supporting frames or shear walls, which then take the loads, wind loads, down to the foundation and the ground underneath. So the wind being transferred from the point of application down to the ground through the floor and roof diaphragms, making this a simple diaphragm building. Most concrete buildings are simple diaphragm buildings. The masonry buildings also can be many times. Wood buildings, it probably are not most of the time. So anyway, simple diaphragm building is where the wind is transferred from the point of application down to the ground via the floor and the roof diaphragms. Okay. There are a number of important conditions under which the simplified design procedure is applicable. Building has to be a simple diaphragm building. Building has to be a low-rise building. I will show you a definition on the next slide. Building is enclosed. I have indicated what that means. Conforms to the wind-borne debris provisions, meaning that the glass is impact resistant. Okay, so enclosed buildings only. Building is regular shaped, and that is defined in section 213 of BNBC. Does not tell you much, but anyway, it's worth reading that definition. I didn't reproduce it. Building is not a flexible building. Okay, so the period is less than or equal to 1 second, not a flexible building. Very important. Low-rise building definition. Enclosed or partially enclosed building. An open building cannot be a low-rise building. Enclosed or partially enclosed building that comply with the following conditions. Mean roof height is less than 60 feet, 18.3 meters. It is also less than the minimum plan dimension. So if the minimum plan dimension is 40 feet, the height cannot exceed 40 feet. Okay, so it's an enclosed or partially enclosed building, mean roof height not exceeding 60 feet, nor exceeding the minimum plan dimension. Very important definition, low-rise. So this simplified procedure is for low-rise simple diaphragm buildings. And the rigid versus flexible, the rule of thumb, as I mentioned in the commentary, we height to minimum plan dimension ratio less than 4 gives you a rigid building. Okay, more than 4 is a flexible building. This is still a good rule of thumb. Building does not have response characteristics, making it. I will let you read number 6. Number 7, the building has an approximately symmetrical cross section. This is very, very important. In each direction with a flat roof or a gable or hip roof, theta less than or equal to 45 degrees, which is plenty steep, but you cannot go beyond 45. Again, the building must be free of significant torsion. That's what it means. The language is kind of complicated. Okay, in this method, the design pressure or suction, as the case may be, is a pressure that is given to you in tables, PS 30, and that has to be multiplied by the I factor, the importance factor. If you're designing a hospital, it will be 1.15. The K sub ZT factor if the structure is not on level ground. If it is up on a hill, K sub ZT shall apply. And the gamma is a conversion factor, because this method, I'll show you where. So this method is for the pressures that are given, the PS 30 is for exposure B and mean roof height of 30 feet. This is why it is called PS 30. Okay? So that number is for exposure B and mean roof height of 30 feet. If you have exposure C, mean roof height of 60 feet above which you cannot go, the lambda factor will convert PS 30 to the value that you should use. Okay, so it is as simple as that. A PS30 for exposure B and mean roof height of 30 feet, you multiply that by I, K sub ZT, and the lambda that converts PS30 to the right exposure and the right mean roof height. So simplified design pressures for main wind force resisting system represent, this is important, the net pressure, sum of internal and external, to be applied to the horizontal and vertical projections of building surfaces as shown here. For the horizontal pressures, P sub S is the combination of the windward and the leeward pressures. Horizontal, the internal pressure cancels out anyway. Okay. And the P sub S value that is given is the combination of the windward pressure and the leeward suction. So this is all you apply on the building. So on the roof, it would be net sum of internal and external pressure. Okay. So this is what is said here is very, very important, and I hope you are following. So horizontal, it is all you apply on the building, the sum of the pressure on the windward face and the suction on the leeward face. The internal pressure doesn't count, it cancels out. But roof, it is the external suction minus the internal pressure of suction. Okay. The net value is given. Okay, wind shall be assumed to come from any horizontal. For the design of the longitudinal main wind force resisting system, use theta of 0 degrees, and I'll show you each. Okay, so this is how this thing works. This is longitudinal wind, designed for longitudinal wind. This is designed for transverse direction of wind. Okay. You divide the surface of the building as shown in the picture, A, B, C, D, E, F, G, H. The width here is 2 times A, lowercase a, and A is defined here. I wouldn't go into the detail, but the point is that this is defined width. So this gives you A and B. A is the wall, B is the vertical projection of the roof, and the interior is C and D. Okay. On the roof, we have E, F, the ridge is the dividing line, and then G and H. For longitudinal direction of wind, theta is to be taken equal to 0, as I just read, and the ridge will be taken as the halfway point of the roof. So this side, it is E and G. That side, the second half of the roof, it will be F and H. Okay. So once these areas are defined, A through H, you can get the pressures PS30 value from this table. Now this crucial table is missing from BNBC 2020. It is just not there. I think somebody found that out, or it was pointed out. Then in the gazetted version, BNBC 2020 actually refers you to figure 6-2 of AC 705 for determining PS30, this table. So the gazetted version tells you to go to AC 705 table 6-2, which is, or figure 6-2, which is what you are looking at for your PS30. So PS30 depends on the basic wind speed, the roof angle, and that's about it. You get the pressure of the suction on all those areas, A, B, C, D, E, F, G, H. Okay. The values are as pointed out for exposure B and mean roof height of 30 feet. So this is as direct as that. The horizontal pressures are, as I mentioned, what we apply on the building, the pressure on the positive, on the windward face minus the suction on the negative face. The vertical pressures consider positive as well as negative internal pressure. The S.Eng they talk about load case 1 and 2. You will never find a definition. So I put it here. Load case 1 means positive internal pressure. Load case 2 means negative internal pressure. This is very, very important. If literally nowhere will you find this specifically said, but that's the meaning. I found out kind of in a difficult, tortuous way. The conversion factor, if you have exposure category other than B, mean roof height other than 30 feet, then you will, all the PS30 values will be multiplied by the lambda that you will get out of this table. Okay, if you have a so exposure B is the benchmark category. If you have exposure C and the mean roof height of 30 feet, 30 feet is 9.1 meters. If you have a mean roof height of 13.7 meters, exposure C, then everything, all the PS30 values have to go up 78%. But the crux of the whole thing is that this is called the windward, the reference corner. And the method tells you each corner of the building shall be taken as the reference corner in turn. If a building is doubly symmetric, then this turning is going to be unnecessary. You will get the same pressure distribution no matter what. If it is singly symmetric, you will turn it once and you are done. You will have all the information you need. But if it is not at least doubly symmetric, then the methods, the simplicity is lost. And so this is why at the beginning it said it has to be approximately symmetric or something like that. Okay, so this is as far as we go with the there is nothing that I left out. Okay, method 2 is the so-called analytical procedure, which is the original procedure from 1972 onwards for rigid buildings of all heights. Actually, these two pages are probably repeat of what has already been discussed or what is to come. So let me start with even this has been covered. So the velocity pressure we have talked about, and the load factor. So this has been okay. So let's start here. This is the analytical procedure in steps. One is you find design wind speed by going to figure 621 of BNBC, and you will see the map in a second. And I showed it to you already earlier. You find wind directionality factor by going to table 6.2.12. You find importance factor by going to table 6.2.9. For each wind direction, you have to have exposure category, and then the case of Z factor, the combined height and exposure coefficient. They're calling it velocity pressure exposure coefficient. So let's look at some of that. The wind velocity will come from this map. As I pointed out, the values range from 41.4 meters per second to 80 meters per second. So anyway, the value comes from this map, and the velocity is in meters per second. Also, to make your life easier, every significant community has been listed in this table. So if you want design wind speed for Dhaka, all you have to do is locate Dhaka, and it tells you 65.7 meters per second. You don't even have to go to the map. So this is additional help that is provided to you. Directionality factor comes from this table, and for all buildings it is 0.85. I don't know that I need to go any further than that. Importance factor, which changes the wind speed from 50-year return period to 100-year or 25-year return period. So for 100-year return period, the importance factor is 1.15. To go down to 25-year return period, if you are in the interior, it is 0.87. If you are in the cyclone-prone region, it is 0.77. And there are reasons for the difference that if there are questions, I will get into. Otherwise, I will leave it there. The combined height and exposure coefficient, K sub Z, which at the mean roof height level is K sub H. I showed you the expression for it. K sub Z is equal to that. Remember, Z sub G, the gradient height depends upon the exposure, whether it is A, B, or C, and alpha also depends on the exposure. Okay, both are given in this table. Alpha, remember, is 7, 9.5, or 11.5, and the gradient heights are 213, 274, 366. Anyway, you can use that equation, or for your convenience, up to 152.4 meters, 500 feet, the values are tabulated for you so that you don't have to calculate. You will get the same values both ways. Okay. Tabulated values you will have to interpolate between the heights that are given. I personally prefer to just go to the equation and calculate my K sub Z. K sub Z at the mean roof height level is K sub H. Then you find topographic effect factor K sub ZT, gust effect factor G, or for flexible buildings it is called G sub F. Enclosure classification that I described to you, partially enclosed, open, or enclosed. Internal pressure coefficient G times C sub Pi, and you will see those values, and external pressure coefficients C sub P, or for the low rise analytical procedure we have G times C sub PF. Those are details, but external pressure coefficient. The K sub ZT, the topographic effect factor, as I said, this is the most complicated one. It is made up of three factors, K sub 1, K sub 2, K sub 3, which are determined from this table and those figures. I have no way of going into that. So the main thing is on flat land, K sub ZT is equal to 1. G, the gust effect factor, as mentioned repeatedly for rigid structures, G is 0.85. For flexible structures, you have to calculate G. I mentioned 13 equations and how much of a pain it is to calculate G for flexible buildings, but there is really no alternative. It does not, nowhere does AC7 tell you that for flexible buildings to be conservative, you can take a G factor of 1.5 or anything like that. You have to calculate, unfortunately, if you have a flexible building with fundamental period exceeding 1 second. Okay, much of what we are doing is repeat. That is the, how should I say, that's to be expected. I discussed the building blocks that give us the design procedure. Now we are putting it all together in our design. Okay, so enclosure classification. I described the classification to you: open, enclosed, partially enclosed. The technical definitions are given here. I am going to skip them because they, in my mind, are not as important as the definitions that I gave you. Okay, so the technical definitions are in terms of how much opening you have on the face on the face of the building receiving positive pressure, and how many openings you have in the entire building envelope. So that this is an open building, typical open building. You see, it's not a building, but this is an open building by ASC 7 definition, and this is an enclosed building by ASC 7 definition. I absolutely want you to see both pictures. Okay? That gas station is an open building, and this parking structure is an enclosed building. Enclosed, again, does not mean a jailhouse without openings on the faces. It simply means it is not a partially enclosed building or an open building by ASCE 7 definitions. Okay, windborne debris region. This, again, I have discussed the definition as well as the fact that glazing on your building, if it is in a windborne debris region, has to be impact resistant or has to have impact resistant covering on it. The internal pressure coefficient depends very much on your enclosure classification. Open building, wind simply passes through, there is no internal pressure buildup. G times C sub pi is equal to 0. Partially enclosed building, look at that, jumps up to plus minus 0.55. Enclosed, as you'd expect, is in between. Enclosed is not an extreme. So there is open building, partially enclosed building, open is 0, partially enclosed is plus minus 0.55. Enclosed building is somewhere in between. It is neither open nor partially enclosed. And the value is plus minus 0.18. I want you to appreciate this. Enclosed is closer to open than to partially enclosed. Okay, and again, most buildings we design are enclosed, and an engineer sometimes goes through a lot of trouble to keep from getting classified as partially enclosed. This is why it's roll down doors. Somebody may claim that it is not an opening. You know, we have instructions in place that it will be closed, and that kind of shenanigans go on. But anyway, these values are kind of important. If you have a large internal volume for a partially enclosed building containing a single unpartitioned large volume, internal pressure coefficient G times C sub pi can be reduced a little bit, and that is a detail that is unimportant. This I have shown you the fact that we consider variation of wind pressure with height only along the windward face of the building. On all the other faces, irrespective of roof shape, we have constant suction most of the time. Sometimes on the windward roof we may have pressure, but all evaluated at the mean roof height level and constant values. Now comes something we have discussed, but we haven't looked at values. Very, very important. The external pressure coefficients. Okay, please pay close attention. This is simple. On the walls, it is simple. Windward wall, irrespective of plan dimension ratio, C sub p is plus 0.8. And on the windward wall, we consider variable pressure. So the 0.8 will go with Q sub Z, pressure at any height Z above ground level. Leeward wall, the C sub P depends on the L over B ratio. L, remember, is the plan dimension parallel to wind. B is plan dimension perpendicular to wind. Between 0 and 1 is negative 0.5. 2, negative 0.3, larger than or equal to 4. The plane dimension parallel to wind is so much larger than plane dimension perpendicular, is negative 0.2. Okay. In between, you interpolate. Okay, if it is 3, it will be 0.25. Side walls, irrespective of anything else, is negative 0.7, the external pressure coefficient. Okay. Now the roof is somewhat more complicated. This is first of all the wind. So no, first of all is this: normal to ridge, where the roof angle is larger than or equal to 10 degrees, and this is normal to ridge, where the roof angle is less than 10 degrees or parallel to ridge. Both are together. Normal to ridge for flatter roofs and parallel to ridge for all theta. This is mean roof height to plane dimension parallel to the wind, H over L ratio. Okay, and for wind normal to the ridge, this is the windward roof, this is the leeward roof. Okay, on the leeward roof, suction only. On the windward roof, it is suction. I think once it gets to pressure here, okay, very steep roofs, just so that you see. Anyway, so you can figure out the external pressure coefficient C sub P for the roof from this table. The upper half is wind normal to the ridge for steeper roofs, theta exceeding or equal to 10 degrees. The lower half, normal to parallel to the ridge or normal to the ridge for flatter roofs. Here there are some interesting things that happen. Let's take this. H over L, so mean roof height is larger than or equal to the plane dimension parallel to the wind. So for the first, so for a length of roof equal to half the mean roof height, you have a suction of negative 1.3. You also have a suction of negative 1.8. Sometimes the lowest suction you need to figure things out. You need the highest value, the lowest value in some applications, not in all applications. Anyway, the highest value is negative 1.3. That can be reduced. That's what the double asterisk tells you. Value can be reduced linearly with area over which it is applicable. So if the area over which the 1.3 applies is 100 square meters or smaller, then there is no reduction. But if it is 1,000 square foot or more, you can take a 20% reduction. So that is not a fixed 1.3. It will be 1.04 when you have the wind acting over 1,000 square meters or more. So there are quite a few details in this table that you will have to spend time looking into and feeling comfortable with, but everything you need is in that table, and these notes to go with the table are extremely important. The table and the notes go hand in hand. Okay, the low-rise analytical procedure is one thing that I'm going to skip. It is pretty similar to the simplified procedure that we looked at. I don't think there is any, you will have any problem if you look at the 3 slides that I'm skipping, figuring out what is happening. Okay, so that's low-rise analytical procedure for low-rise buildings. Okay, so the next step is figure out the velocity pressure Q. So remember 000613 V squared K sub Z, K sub ZT, K sub DI. We have all the factors by now. We have looked at all of them. Okay, so at this stage we should be able to calculate Q. Now this is now the bottom line. Okay, and I may or may not get through every line on the next slide, but this one I do want to cover. So if we have a rigid building, irrespective of height, okay, the analytical procedure itself doesn't really have a height limit on it. There are other things in AC 7 or its commentary that tell you that, for extra, like if you calculate a cost factor of 2, do not use the analytical procedure. And there are things like SAID here and there, but the analytical procedure does not come with a height ceiling in it. So if it is a rigid building, any height, the pressure due to wind is the external pressure QG C sub P minus, as we have seen, Q sub I, velocity pressure for internal pressure, times G C sub Pi. This is the number that is either plus minus 0.18 for enclosed buildings or plus minus 0.55 for partially enclosed buildings. Q sub I have mentioned to you, we typically take as Q sub H. Okay. So when we are designing the overall building, the horizontal pressure, the internal pressure term cancels out, doesn't matter. What we apply on the building is positive pressure on the windward face minus the suction on the leeward face. Okay? But if we are designing the roof or the roof members, then we apply this equation as it is. And remember, we have to consider positive internal pressure as well as negative internal pressure. Okay? Now, if it is a low-rise building, remember, mean roof height not exceeding 60 feet, nor exceeding the minimum plan dimension. And it is not an open building, it is enclosed or partially enclosed. The low-rise analytical procedure is what I skipped. In that procedure, even on the windward face, we do not take Q sub Z, variable wind pressure. It is all Q sub H, all faces. Okay, and the G times C sub P is now G times C sub PF. Okay, it is a lumped together value that is given in the tables that I skipped. And the internal pressure term is as before, no change from here to there. Okay, this is what is different for this part, is different for low-rise buildings, the so-called low-rise analytical procedure. The low-rise buildings you can design by that procedure, absolutely allowed. This is for any height. But there is this low-rise analytical procedure, the specialized thing that I skipped there. There is no Q sub Z anywhere. It is Q sub H on all faces. And instead of G and C sub P separate, we are given G times C sub PF lumped together in tables. Okay. If it is a flexible building, then the G becomes G sub F. And that's about the only change. This is a calculated, remember, gust factor that will be very painful to calculate unless you have a spreadsheet or something in your design office. And then for parapets, there is a G times C sub P.Eng given, which you multiply by the velocity pressure at the top of the parapet. Okay, so that is some detail that you will have to look up. What I just said is probably not sufficient, but there is a separate coefficients of P.N that I wanted to draw your attention to. Now, for components and cladding, I am tempted to tell you to basically read it by yourself. If you understand this, you will understand that. You will have to spend some time. It's a level of detail that I even hesitated about including, but then I thought that it would be good for you to have it all in one place. So this is the only reason that I included this. So I think time will be better spent if I take 5 to 10 minutes, no more, on this wind tunnel procedure, which is method 3. Wind tunnel testing is a powerful tool for the engineer, and most important buildings, I would say. In Chicago, any building over 20 stories is designed based on wind tunnel testing. That's because you get to design for lower wind pressures that way than what ASC 7 will give you. Okay, so can be used on any building. ASC-BNBC 2020 only covers along wind load effects. That is one limitation of the analytical procedure. If you want across wind effects to be captured, you need to go to wind tunnel testing. The wind tunnel testing is essentially required for highly unusual shapes. The analytical procedure is really for box-like structures. We try to fit it to the actual shapes that we design, but that is not easy to do beyond a point. If it is highly unusual shape, then wind tunnel testing is about the best thing to do. Unusual response characteristics, that would be the case with highly flexible buildings. Then we should not try to use the analytical procedure. And then all the across wind phenomena, vortex shedding, galloping, those, if you want to capture those, then you need wind tunnel testing. Now, in the commentary of ASC 705, these things have all evolved. There is now a wind tunnel test standard that ASC publishes, but all of that for you is in the future. So in ASC 705, in the commentary, ASC's Committee 7 told you when you design based on wind tunnel testing, do not go below 80% of the values that ASC 7 would give you for your main wind force resisting system. And also for components and cladding, do not go below 80% of the values that you will get for zone 1 of roofs and zone 4 of walls. That zone 1 is the interior of the roof, zone 4 also is the interior of the walls. Anyway, details aside, ASC 7 felt it necessary to warn you in the commentary not to go too far below the ASC 7 values when you do wind tunnel testing. This is back in the days when wind tunnel testing was not standardized. So wind tunnel procedure is used for shapes that are not box-like, for flexible buildings, for slender buildings, buffeting by upwind structures. So upwind structures may do things to your structure, and that has to be captured. Accelerated flow from channeling by buildings or topographic features. That happens. If a narrow gorge could be between two tall buildings, between a building and a hill, and that you may end up with higher. If wind has to pass through a narrow passage, the velocity will go up. And if your building is right at the end of that passage, then you may be looking at problems. The The cladding loads, some of these things are probably a little bit repeated. Let me talk about cladding pressure because there is design of the cladding itself, and then there is design of the cladding, of the connection between the cladding and the structure, which is more important in many ways. And for both, you need the wind suction on the cladding. The best way to get that is through wind tunnel testing. And it is used pretty widely for that purpose. Even though the structure may be regular, you don't particularly need wind tunnel testing for the design of the structure. Considering the cladding and its importance, that the importance of having the cladding connected to the structure in a severe wind event, wind tunnel testing is done just to figure out the cladding pressure. So that is not at all uncommon. And wind tunnel allows you to simulate the actual wind pattern. So this is for the city of Dallas. Record over many, many years shows that you see what it shows. Depending upon the direction, the wind speed increases or decreases. And this you can simulate in the wind tunnel. It's very, very difficult to analytically do so. There are times, like you go through two tall buildings or even enter a tall building, you feel the wind. If you have loose clothing on, the clothing wants to come off. There is pedestrian comfort, people who are walking around tall buildings, and all of those things can be figured out beforehand, before the structure goes in place, by proper wind tunnel testing. So this gives you reasons why wind tunnel test results typically comes out to be less than given by ASC 7 analytical procedure. I have a few pictures that you may find of interest, and that's after that I quit. So this is the building that is being tested in the wind tunnel. Typically that building will be modeled now in wind tunnel testing. The scaling down of the buildings is the most important thing. So you typically do not test only the building, but essentially the neighborhood, because the neighboring buildings affect wind flow on your building. And you also can play what if scenarios. What if this neighboring building were to disappear 5 years from now? What if another building would come somewhere in that vicinity 5 years from now? So you can you can take one of, anyhow, this will be made of a different material, heavily instrumented. All the neighboring buildings will be to proper scale, but they are of inferior material, cheaper material, and not instrumented. Okay. The carpet simulates the roughness of the terrain, and you can change the wind velocity, and by rotating the models you can change the wind direction. Okay, this whole thing will be on a table or something that is possible to rotate. So these are the basics of wind tunnel testing. This is Jack Cermak, one of the pioneers of wind tunnel testing. Okay, so this is the same thing. The building that is being designed and the neighborhood all scaled for wind tunnel testing. This is a power station right on the side of a gorge. There is absolutely no way to design something like that without wind tunnel testing. This is the you remember in front of the loop, I.M. Pei designed this pyramid, and this is the wind tunnel testing of the pyramid together with the older structures, including the loop. So this is kind of a historic picture, but this was the basis of the design of that very important new pyramid. So that gives you at least a very basic idea of what can be done and is done with wind tunnel testing. So hopefully, as I said, it is tough in 2.5 or 3 hours to cover this enormous subject, but hopefully this has been beneficial. Thank you. I'll stay for I don't know, maybe 15, so up to 10 after 11 to answer your questions.
Thanks, Dr. Ghosh. Yeah, like most of the questions I answered.
Good.
Well, I will start with the ones that I didn't. Okay. What should be the connection detailing between the periphery brick wall to MWFRS steel and RCC buildings?
So you are talking about brick cladding on concrete or steel buildings. Okay. I don't know that there is one answer to, yeah. I don't know. I may not be the best one. Maybe refer this question to Dr. Rakib, because it has to be what is locally done. So
okay, so I will just ask him
yeah,
to send it to support.
send it to him. I think he will be.
Okay.
His answer will be more beneficial.
Okay. Do we need to apply load on wall based on solidity ratio of for an open building?
Read that again.
Do we need to apply load on wall based on solidity ratio for an open building?
I do not know what solidity ratio of an open building is, and
I think by solidity he's meaning that open area to closed area, I guess, that ratio.
Open buildings, as I kept on saying, 80% of each space basically open, at least 80. So it is mostly open. I do not know what a solidity ratio would be. And for open buildings, there are design coefficients given in AC 7. I think you will be better off looking at those. I do not have an answer to the specific question because I don't understand it.
Okay. Can we design for wind using all heights method for a low rise structure?
Yes, absolutely. Absolutely. That's what all heights mean.
Yeah. Dear sir, for arched roof, open structures, and multi-gable structures, which provision of BNBC and AC will be applicable?
Say that one more time.
For arched roof, open structures, and multi-gable structures, which provision of BNBC?
Mighty gables, what's the word?
Multi-gable.
Oh, multi-gable. Okay.
Yeah.
So arched roof and multi-gable structures. These are open structures. Okay.
So which provision of BNBC and AC will be applicable?
Yeah, AC open structures, without looking, I do not know. Give me. I these things come once in a while, so it's difficult to remember. Open structure, multi-gable or domed, I do not see, or arched. At least offhand, I do not see given in AC 705. Enclosed, partially enclosed, there is domed roof. Anyway, it is pretty easy to take a look at what AC7 has, and the same is true of BNBC. If it is not there, then I things have been added in subsequent editions of AC7. I can look there if anything has been added, and this we can communicate to you. But in case it has not been, then you are left to your own devices. You have to go to the internet and see. Maybe the Australian code has something. Australian code is pretty advanced in wind, so many times you will see things there that are not anywhere else. But be careful. Their averaging time is different. So the coefficients may apply. Some of the stuff you have to be careful in importing. So with that little caveat, I would suggest that you will probably need to look at a place like that. This is not something you can figure out. You know, somebody has to have researched it and come up with numbers.
Okay. So AC75 wind load cases with torsional load effects makes the wind load complicated.
Yes.
Can you tell me how it will be applied in buildings?
Yeah, this I didn't even go into today. The 3 hours I had a lot of decisions to make. Anyway, unfortunately, and again, because of the edition, I do not know. We started out by requiring that buildings beyond a certain height be designed for 4 different load cases, and the idea was to have wind-induced torsion. One of the load cases is half the face of a building loaded with full wind and half the face not loaded at all with wind. Then pretty quickly, the requirement was extended to buildings of all heights, not just tall buildings. AC 705 probably, by AC 705, we probably were already there. So every building, at least theoretically, has to be designed considering the 4 load cases. But then there is an appendix that has been developed. Which appendix is it? Appendix D, is it? Yeah. Anyway, the question is a good one, and I will put up a short written answer. I do not see it. I think it is Appendix D, and it may have come later than AC 705. So there is an appendix that has been developed. If your building complies with the conditions given in that appendix, then 2 of the more problematic load cases go away. You are left with only 2 out of 4 load cases, which are the 2 simpler load cases. So this is how it has been handled, but all of that may not have happened. This is my problem with AC 705, then AC 710, then AC 716, now AC 722. And you know, for me to remember what was in AC 705 and not in AC 705 is kind of tough. So I would rather look and post a written answer, but the basic answer is what I gave you, that yes, 4 load cases have to be considered. It started out only for the taller buildings, but then it extended pretty quickly to all buildings. And 2 out of the 4 cases you can get exemptions from if your building complies with this Appendix D. That's yeah, but Appendix D may not have been in SC 705. We'll look that up.
Okay, Dr. Ghosh. If a building meets the condition of partially enclosed with respect to one wall, is it necessary to provide partially wind condition with respect to other walls, or only apply the partially enclosed wind on the governing wall?
This one wall thing, I don't know is the right way to think. Let me think for a second. So the better way to think is wind direction. Okay, so for one wind direction, you may have partially enclosed situation. For another wind direction, that may change because the classification depends upon the openings on the face with positive pressure and on openings in the entire envelope of the building. So depending upon which face is receiving positive pressure due to wind, the enclosure classification may change. So you may have to consider different enclosure conditions for different directions of wind. That is the answer that I want to give you. To think wall by wall, I do not quite understand. Maybe it makes sense, but I have to I have to I have to see that. I do not know.
Direction makes more sense.
No, it is that the direction definitely is the way the requirements are framed. It is always by definition the wall receiving positive pressure. So how many openings are on that wall versus how many openings are in the total envelope. That's what defines the enclosure classification. So it definitely is dependent on the direction of wind.
Okay, so moving on. If we calculate the net pressure at any level of a building, what is the effect of positive or negative internal pressure? As we know, the sum of internal pressure will be zero because it works in the opposite direction in leeward and windward side.
Yeah, so I kept on saying in the if you are calculating deflection for your building, the internal pressure doesn't play any role. Okay, but if you are designing a wall of your building, then the wall is acted upon by a if it is windward wall, it will be acted upon by pressure from the outside and a pressure or a suction from the inside. And the wall will experience the net effect of both. And you have to consider that. And then when the wind direction changes, it will be the suction wall. So you have to consider all. So what I'm trying to say is that you have to consider different wind directions, but in the design of the components, whether it's the wall or the roof or whatever, you have to consider both the external pressure and the internal pressure, because the component will feel the net effect of both. Okay? So overall design of the building, internal pressure goes away, but in the design of the components of the building, internal pressure does play a role.
Right. So one question is, what is the best software for wind tunnel testing? So I would just rephrase it, like, can we use software for wind tunnel testing?
Software for wind tunnel testing? What does it mean?
Dr. So nowadays they have like CFD analysis and stuff, where you can replicate the wind tunnel testing through a software, but I don't think that is allowed by code or something like that.
Not to my knowledge. I have never known of something designed on the basis of simulated wind tunnel testing. I haven't come across that. I didn't know that it existed. Wind tunnel testing is always physical testing. People wait 6, 8, 9 months to get in. There aren't too many labs even in the US, and they're almost always busy. But I haven't known people simulating, and that wouldn't be acceptable to building departments here. I can tell you that.
In structural, second, let me rephrase it. We detail for seismic loads, but why don't we have special detailing for wind loading?
It's very simple. We design our structures to remain elastic under the design wind forces. We design our structures to go inelastic deliberately under the design seismic forces. The inelastic deformations to accommodate them, to make sure that the inelastic deformations do not cause collapse of the structure or partial collapse. We have to have fancy detailing. As long as structure is elastic, we do not need fancy detailing. So it is very basic but very simple. And this is something you always need to understand. Wind design, and up until now, is elastic. There are now recommendations, and I think AC even has published a document recent times, performance-based wind design, where under hurricane forces they are talking about doing what we do for earthquakes. Let the structure yield in places. But that is definitely in the future, okay, not now. Wind design so far is elastic. Seismic design has not been elastic for probably 100 years now or more, pretty much from the beginning. So that's a very fundamental difference.
Yeah, that's probably the best answer that you will get to this question.
Mm-hmm.
And this is also very fundamental. If calculated gust factor is greater than 0.85, can we reduce wind load factor of 1.6 in load combinations?
Say that again.
If the calculated gust factor is greater than 0.85 for flexible buildings,
yeah,
can we reduce wind load factor 1.6 in load combinations?
No. One has nothing to do with the other. I don't even understand how the question arises. I don't know. No. Answer is no. Okay, it's approaching a quarter after. I think we probably...
Yeah, I'm just looking at the questions. Let me see if there is one or two that is...
Wind design is not an easy subject. It's
room 2 also, Dr. Ghosh.
Say that again.
Room 2 questions, just one or two room 2 questions. I will then end the session.
Yeah.
There are no formula in BNBC to calculate time period T for wind analysis.
That is true. This is what I tried to point out. This is why I brought in AC 710. So the formulas are in AC 710 in the main body, or if you have AC 705, the formulas are in the commentary. But BNBC is based on AC 705, not the commentary, so the formulas are not in BNBC. So you can use the formulas from the slides or go to AC 710 or AC 705 commentary.
Yeah, there is one more question about solidity ratio. So I don't know if...
Yeah, there must be something that I don't know about. I have heard the term, but I don't know what it is.
Maybe in BNBC they have defined something. I have asked them to mail support. We can ask Dr. Rakib about it.